History. In 1939, Martin Kamen and Samuel Ruben of the Radiation Laboratory at Berkeley began experiments to determine if any of the elements common in organic matter had isotopes with half-lives long enough to be of value in biomedical research. They synthesized 14 C using the laboratory's cyclotron accelerator and soon discovered that the atom's half-life was far longer than had been previously thought. This was followed by a prediction by Sir J. Koff, then employed at the Franklin Institute in Philadelphia, that the interaction of thermal neutrons with 14 N in the upper atmosphere would create 14 C. Note 134. It had previously been thought that 14 C would be more likely to be created by deuterons interacting with 13 C. 1. At some time during World War II, Willard Libby, who was then at Berkeley, learned of Koff's research and conceived the idea that it might be possible to use radiocarbon for dating. 3.4. In 1945, Libby moved to the University of Chicago, where he began his work on radiocarbon dating. He published a paper in 1946 in which he proposed that the carbon in living matter might include 14 C as well as non-radioactive carbon. 5.6. Libby and several collaborators proceeded to experiment with methane collected from sewage works in Baltimore, and after isotopically enriching their samples they were able to demonstrate that they contained 14 C. By contrast, methane created from petroleum showed no radiocarbon activity because of its age. The results were summarized in a paper in Science in 1947, in which the authors commented that their results implied it would be possible to date materials containing carbon of organic origin. 5.7. Libby and James Arnold proceeded to test the radiocarbon dating theory by analyzing samples with known ages. For example, 2 samples taken from the tombs of 2 Egyptian kings, Zoser and Sneferu, independently dated to 2625 BC plus or minus 75 years, were dated by radiocarbon measurement to an average of 2800 BC plus or minus 250 years. These results were published in Science in December 1949. 8.9. Note 2. Within 11 years of their announcement, more than 20 radiocarbon dating laboratories had been set up worldwide. 11. In 1960, Libby was awarded the Nobel Prize in Chemistry for this work. 5. Physical and chemical details. In nature, carbon exists as 3 isotopes, 2 stable, non-radioactive carbon-12-12 C and carbon-13-13 C and 1 radioactive carbon-14-14 C, also known as radiocarbon. The half-life of 14 C. The time it takes for half of a given amount of 14 C to decay is about 5,730 years, so its concentration in the atmosphere might be expected to decrease over thousands of years, but 14 C is constantly being produced in the lower stratosphere and upper troposphere, primarily by galactic cosmic rays, and to a lesser degree by solar cosmic rays. 5.12. These cosmic rays generate neutrons as they travel through the atmosphere, which can strike nitrogen-14 N atoms and turn them into 14 C. 5. The following nuclear reaction is the main pathway by which 14 C is created. N plus 14, 7N, right pointing arrow 14, 6C, plus P, where N represents a neutron and P represents a proton. 13-14. Note 3. Once produced, the 14 C quickly combines with the oxygen O in the atmosphere to form first carbon monoxide CO14 and ultimately carbon dioxide CO. 2. 15. 14C plus O2 right pointing arrow 14CO plus O. Carbon dioxide produced in this way diffuses in the atmosphere, is dissolved in the ocean, and is taken up by plants via photosynthesis. Animals eat the plants, and ultimately the radiocarbon is distributed throughout the biosphere. The ratio of 14 C to 12 C is approximately 1.25 parts of 14 C to 10-12 parts of 12 C. 16. In addition, about 1% of the carbon atoms are of the stable isotope 13 C. 5. The equation for the radioactive decay of 14C is 17 14 6C Right pointing arrow 14, 7n, plus, A minus, plus, nu, A, by emitting a beta particle, an electron, A minus and an electron antineutrino. Nu, A, one of the neutrons in the 14. C nucleus changes to a proton and the 14. C nucleus reverts to the stable, non-radioactive, isotope 14. N. 18. Principles. During its life, a plant or animal is in equilibrium with its surroundings by exchanging carbon either with the atmosphere or through its diet. It will, therefore, have the same proportion of 14. C is the atmosphere, or in the case of marine animals or plants, with the ocean. Once it dies, it ceases to acquire 14. C, but the 14. C within its biological material at that time will continue to decay, and so the ratio of 14. C to 12. C in its remains will gradually decrease. Because 14. C decays at a known rate, the proportion of radiocarbon can be used to determine how long it has been since a given sample stopped exchanging carbon. The older the sample, the less 14. C will be left. 16. The equation governing the decay of a radioactive isotope is 5. Asterisk, wherein 0 is the number of atoms of the isotope in the original sample at time t equals 0, when the organism from which the sample was taken died, and n is the number of atoms left after time t. 5 lambda is a constant that depends on the particular isotope. For a given isotope it is equal to the reciprocal of the mean life, i.e. the average or expected time a given atom will survive before undergoing radioactive decay. 5. The mean life, denoted by tau, of 14. C is 8,267 years. Note 4, so the equation above can be rewritten as 20. Asterisk. The sample is assumed to have originally had the same 14. C 12. C ratio is the ratio in the atmosphere, and since the size of the sample is known, the total number of atoms in the sample can be calculated, yielding N0, the number of 14. C atoms in the original sample. Measurement of N, the number of 14. C atoms currently in the sample, allows the calculation of T, the age of the sample, using the equation above. 16. The half-life of a radioactive isotope, usually denoted by T1/2, is a more familiar concept than the mean life, so although the equations above are expressed in terms of the mean life, it is more usual to quote the value of 14. C's half-life than its mean life. The currently accepted value for the half-life of 14. C is 5,700 plus or minus 30 years. 21. This means that after 5,700 years, only half of the initial 14. C will remain, a quarter will remain after 11,400 years, an eighth after 17,100 years, and so on. The above calculations make several assumptions, such as that the level of 14. C in the atmosphere has remained constant over time. 5. In fact, the level of 14. C in the atmosphere has varied significantly, and as a result, the values provided by the equation above have to be corrected by using data from other sources. 22. This is done by calibration curves discussed below, which convert a measurement of 14. C in a sample into an estimated calendar age. The calculations involve several steps and include an intermediate value called the radiocarbon age, which is the age in radiocarbon years of the sample. An age quoted in radiocarbon years means that no calibration curve has been used minus the calculations for radiocarbon years assume that the atmospheric 14. C12. C ratio has not changed over time. 23-24. Calculating radiocarbon ages also requires the value of the half-life for 14. C. In Libby's 1949 paper he used a value of 5,720 plus or minus 47 years, based on research by Engelkemir et al. 25. This was remarkably close to the modern value, but shortly afterwards the accepted value was revised to 5,568 plus or minus 30 years, 26, and this value was in use for more than a decade. It was revised again in the early 1960s to 5,730 plus or minus 40 years, 2728, which meant that many calculated dates in papers published prior to this were incorrect. The error in the half-life is about 3%. Note 5. For consistency with these early papers, it was agreed at the 1962 Radiocarbon Conference in Cambridge, UK to use the Libby half-life of 5,568 years.